Welcome to 14th lecture. We are studying chapter number 9, VLSI design, and we will continue studying dual rail logic in this lecture. And before we start, there is a recap. Let's recap from our last lecture. We studied case code voltage switch logic. It's a kind of dual rail logic that we implemented in last lecture. We implement logic gate and then two. We implemented the regular NMOS array here and the complement of the array here, or the expression we get here. We apply De Morgan's law to it, and then we implement the resulting array here. So a different thing that we have different a thing that is specific to the dual rail logic is that now we have two outputs and they are complement of each other. So if we get F here, F here, we get F bar or F complement here. So before we study exclusive or exclusive NOR pair using the same technique, we will learn about logic trees. In this lecture, we'll study logic trees. So what a logic tree is, the same circuit can be thought of implemented using a logic tree. How? Right. We have A and B transistors connected together, and whatever is implemented here is, since they are connected in series, so right here we have their AND operation A and B because they are in series. But the functionality that we'll get here at this terminal is the complement of that. This is because in a regular CMOS circuit, when we implement NMOS, we compute a complement of the original expression that we studied in chapter number 7 and 8. Right. So whatever we get here, in this case, this is the ANDed, this is the AND operation between A and B ANDed. We get a complement of that here. Similarly, here we have A bar and B bar, and they are connected in parallel. This means there is an OR operation between the two. And if we apply De Morgan's law, if we apply De Morgan's law here, so we get A and B ANDed with one single bar. And whatever we get here is the complement of what we get here using this combination, and that is of course the AND operation AB. So this is what we get here. So in short, whatever is the functionality implemented using NMOS array, the output that we get on the upper terminal is the complement of that. That's very important. So this helps us in implementing exclusive OR and exclusive NOR circuitry with ease. How? Let's see. Let's see how. Exclusive OR operation can be written as A complement B or A B complement, whereas exclusive NOR operation is the complement of that. And if we solve it using the Boolean algebra techniques that we studied in elementary courses, we get to the point where it is A complement B complement plus A and B, right? So we have in both expressions, we have A and A complemented, A and A complemented, and B complemented. Here we have B and B complemented. So we'll start with any one. We can start the tree. We can start building the tree using any of the two variables, either A or B, because A and B, though they both are present in all terms. Here we have two terms, they both are available there. So therefore we can either start with B, we can start this tree by putting A at the root or B. It doesn't matter. So we'll start with A here, and we can start with B. So, and here we have this B bar and B terminals, and then B bar and B transistors. So A bar ended with B bar, right? A bar. Let's see what this exclusive OR operation is. A bar Let's take all this in the picture. A bar, B bar. So here we have A bar, B bar, right? And from here we had A, B plus A, B. This is the expression that we obtained for exclusive NOR. But here we are getting exclusive OR. Why? Because whatever we get here is the complement of this. That is, we know from the regular CMOS implementation. And similarly, for exclusive NOR, it can be shown that it is A bar B. At exclusive NOR, we get A bar B plus A B bar. A B bar. So this is an expression for exclusive OR, but whatever we get here is the complement of that. That's right. So it can also be represented in terms of this pair of A and A bar can also be represented in the form of a rectangle with minus and plus terminals. Minus means we have an NMOS transistor. We have an NMOS transistor with negative, with complemented input here, and an NMOS transistor with non-complemented or the actual output at this terminal, and we can write it A. So similarly, we can represent B and C and any other variable like this. So it's a shorthand notation of having these two transistors as a pair. Right. Now we have another example to solve where we are given this truth table, and we know that for this it is 1 for this input combination and this and this. For these four input combinations, the output is a 1. So we can write it like this, or we can put it in a Karnaugh map, K map. And when we solve it using K map, it turns out to be A bar B, because this one is A bar and we have both values of C, therefore is A bar B, and this is B C bar because we have both values of A, so this is B C bar, and this is not going to make a pair with anyone, so therefore we'll write it A B bar C. So if you implement it using the shorthand notation that we have developed here, it will be implemented like this. Let's take all these things in the picture. Let's take everything in the picture right now, like this. Now we have everything here, A bar B. So we have in these three terms, we have B and B bar common. So we'll put B at the root. This is very important. Instead of A, we'll put B at the root because we have B here, here, and here. In all three terms, we have B in all three terms. Therefore, we'll put B in the root. We cannot put A or C in the root because otherwise implementing A bar B would be a problem. So to develop a tree, we first have to decide which of the 3 or 4 variables that we have to put which variables at the root. So here we have to put B in the root, and then B ended with A bar, right? B ended with A bar. So B ended with A bar, this one. B ended with A bar, and then B ended with C bar. B ended with C bar. So this is B, this is its AND operation with C bar, and then A B bar C. So we take A B bar C. So this is B bar and taken to C, and the output B C is taken to A, and we have A B bar C here. B bar C here. Here we have B C bar. B C bar, and on this line we have B A bar or A bar B. B A bar or A bar B. So that will not implement F. This is very important. Although we have written everything or we have developed the scheme for F, but it doesn't implement F. What is it what does it implement? It implements F bar because NMOS arrays puts implements the complement of original expression. And in the same way, we can implement its complement. If it is F bar, this must be F. So with this red color, I have implemented F. But to find out the expression for F, we have to implement, or we have to make make we have to develop an expression for the complement of F. Now we have fonts at places where we initially had zeros in this K map. Now we have ones replaced with zeros and zeros replaced with one to make it a complement of F. And then we have solved again using the same K map technique that we developed in earlier courses, and we come up with this expression, right? We come up with this expression, and once we implement it using, and I have implemented it using this red color, we get an F. We get F here, right? That's all for today's lecture. In our upcoming lectures, we will keep on studying more about high-speed VLSI circuits. Thank you.